Alright, moving on to number 5. In number 5, we have a compound gear train. Alright. So that means at least two of gears are on the same axle. 4 gears, same number of teeth as the problem above. Alright, so we had an A with 10 teeth. Number of teeth on gear B was 20. Gear C was 5. And gear D was 40. Alright. Gears B and C share the same shaft. So if that's 10, gear B is 20, gear C is 5, and those are on the same axle right there. And gear 40 would mate with gear sorry, not 40, but gear D. I should have drawn that larger, but that's D, that's C, that's B, and that's A. And this is our input, and this is our output. We got to treat this a little bit differently. Actually, let me draw bigger at D, because that's going to mess me up. I'll go off the screen a little bit, at least that'll be true to life. There we go. Alright, so with compound gears, you're always, at least 2 of these are sharing the same axle. A is driving B. B and C have to rotate together. They have the same angular velocity. And then C is driving D. Alright, so how many times will gear A rotate compared to gear D? So again, we want to find the angular velocity of A compared to the angular velocity of D, in over out. Now, that's going to be equal to our gear ratio. So we need to find that gear ratio. But for this, since we have 2 of these, we need to go out over in for A and B, and out over and in. It's not just for A and D now, because A and B are simply put together. So this is out is B, in is A, times, multiply these. Actually, let me write it this way. Back up a step. The gear ratio for the whole thing is really the gear ratio between A and B times the gear ratio between C and D. So we need to look at that. Alright, so between A and B, we have an out over an in times, again, for C and D, an out over an in. So the out for G would be B. So 20 teeth. A is the input, that would be 10 teeth, times output for C and D would be D, so that's 40 teeth. In would be C. C is driving D. Output. So that would give us 20 over 10, which is 2, times 40 over 5, which is 8, or a gear ratio, an overall gear ratio of 2 times 8, 16. So that's our gear ratio. Now our gear ratio is also equal to the angular velocities, comparing the angular velocities. Our gear ratio is 16. That means the angular velocity of the input compared to the angular velocity of the output is 16. So A is going to spin 16 times for every time D will spin. So gear A, 16 times. Gear D, 1 time. Every 1 time the gear rotates around, gear A is spinning faster. Now we're losing angular velocity, but because of that we're gaining torque. There is a trade-off there. So the faster the output spins, you're not getting anything for free. You sacrifice torque, its ability to turn harder things to turn, by gaining speed. So it spins faster, you lose torque. If you slow it down, you gain more torque. This can move something more difficult to move. So, alright, if 10 foot-pound of torque is applied to gear A, what's the output at D? Well, the gear ratio is 16, like we said. So gear ratio is also equal to torque out over torque in. So our gear ratio is 16. Rid of this. Our torque out, we don't know, trying to find that. Our torque in, we said, was 10 foot-pounds. So, times 10, times 10, cancels out on this side. We have 160 foot-pounds of torque coming out at gear D. So it's spinning not as fast, but we're gaining much more torque, 16 times as much torque as we were before.